morning, everyone. This is going to be the SmartVisionLights Basic Machine Vision Lighting Training Module 2. I'd like to, on behalf of SmartVisionLights, I'd like to welcome everyone today and thank you for attending. My name is Steve Kinney and I'll be your presenter today. We're going to today cover specular versus matte surfaces and the challenges required in dealing with those solutions. So for those who have watched or attended our last presentation, in our last module, we examined how the positioning of lighting affects the image. Largely, we talked about bright field and dark field lighting geometry. So we can see from the slide I brought forward here that the position of the lights affects whether we get a bright field or a dark field image, and that these images are inverted. And the positioning and structure of the lights are very important to the type of image that we get. Today, we're going to look at how the surface properties of the object itself can affect the lighting. So not only the light geometry and type of light we use and the position of those lights, but the object itself can affect how we choose and position those lights. So to begin with, light has interaction with surfaces in four basic ways. Either light comes to the surface and hits the surface and reflects off the surface. It hits the surface and is scattered off the surface. It may be absorbed by the surface when it hits and very little light is reflected or scattered off the surface. Or it may penetrate the surface and actually refract through the surface. Some important things to remember is that when light does strike a surface and bounce off of it, that the angle of incidence equals the angle of reflection. This principle always applies as we're talking about lighting. Secondarily, when we talk about refraction, if we are not going to bounce off the surface, but we're going to talk about what penetrates the surface, then we need to remember that light that is refracted moves towards a denser medium, and that you will see an offset between what you're seeing outside and through the medium. So you can see in our example here with our person in the pool and his physics is fun sign that his body seems to be offset from his head, but that is because the light from the perception of the viewer is striking the surface of the water, which is denser than the air that he's standing in, and that the light is then bent towards the denser medium, which is down towards the water in this case. So you see either in the fish diagram there or the man in the pool that the light that you perceive is bent from where the object is in real space. Solid surfaces may be somewhere between reflective and perfectly amorphous or matte. You can see that light will bounce off shiny surfaces, but unless it's a chrome-plated ball bearing as we have here, or some other very reflective surface mirrors that we're going to talk about coming up here, then usually we actually get a combination. So nearly perfectly reflective surfaces are called specular, and we talk about specular light or specular reflections. We're talking about good mirrors, things that are either polished metal, liquids at low angles, mirrors themselves. Shiny parts are very common in machine vision because we're all looking at electronics with screens or machine parts or other types of things, vials for medical applications. So these are all referred to, all these are reflective surfaces, but are called specular. And again, when you have a very specular surface, the incoming rays of light with a very high efficiency are bouncing off the angle of incidence that they're striking the surface at. They're bouncing at an equal and opposite angle. The opposite of this is what we call matte, or also called amorphous surfaces. And amorphous surfaces then are very good at scattering the light. So light comes in and strikes the surface, but it produces a diffuse reflection, and that's because the light is not absorbed by the materials reflected, but the surface is such that it doesn't reflect in a coherent manner as on the mirror or the specular surfaces. So perfectly matte surfaces can be things like white paper, often powders, ceramics, or those kind of things are very good at this, and they produce a pure diffused reflection. It doesn't really matter then as much where we put the light. In matte surfaces, then it's very important we get a uniform lighting and in a structure that we want, but they are much more forgiving, and if you have a matte surface, an object with a matte surface that you're trying to inspect, you'll find your window for getting good lighting is much bigger. So this is the difference between a mirror and a sheet of white paper, the difference between specular and matte, and you'll see in the examples we're going to carry that forward a little bit and use those two extremes to demonstrate what we need to talk about today. So when we talk about real surfaces again and machine vision, then many of these surfaces are not, in fact, perfectly matte or perfectly amorphous. They might be specular but have multifaceted, so they might have reflections in the sharp grooves here but have a less reflective face to them. You may have a rough surface on the micro level that's actually scattering light, even though it's more mirrored on there. Each of these mirrors is at a molecular level at a very different angle, and it actually can be, even though it's shiny at molecular level, can also be very amorphous. Things like a surface where we have water or other beads on there can be challenging, but can also be a combination surface where the background may not be as specular as things like the water droplets on the surface. This also applies to things like coated paper, texture paper, molded plastic parts, machine parts. Again, there you may get some combinations. A lot of light may hit the surface and bounce off, as in this black vector here, but much of it may also scatter, as in the gray vectors there. So often the real world is a combination on the object you're inspecting, and you get a combination result. However, what you're going to find, and what I'll show you here, is you're mostly concerned about the specular surfaces, because again, if you have a combination result, the matte part of the surface is then much more forgiving, and it's usually the specular part, such as if we look at this blue sheet of paper, you're trying to get the glare out of the corner where the rest of the surface is very good. So we are going to look at several things today, but you will see we are going to focus on the specular parts. So to begin with, we have set up an example here with a matte surface. Again, a very common and very good matte surface is a sheet of copy paper. So at the surface, the copy paper is actually a little bit rough. It absorbs a little light, and where the light is striking the surface is scattered very evenly. So you can see in the setup, we have a Cognix camera, and we have 4 SmartVision L300 lights arranged in a square so that we have very even and uniform bright lighting. And you'll see it's very easy then to get uniform lighting on our piece of paper with some targeting on here, for example, and that simply getting a good image here is a matter of establishing good lighting geometry, practicing good techniques, and having uniform lighting. There's nothing really special to do a good matte surface like this. Conversely, though, if we take something now and say that we want to inspect something like a automotive application where they're looking at a rear view mirror in a car, we now take the same exact setup, which was previously giving us very uniform lighting and a good image, but now we put the mirror under there. And even though we have the same setup and the same uniform lighting, you can see that what we see in the object probably is not what we want to actually inspect. We want to look at the surface of that mirror to see things. There's a variety of reasons why people use mirrored surfaces. Or again, the real world example, this might be a machine part with a highly polished surface or the chrome ball bearings, but the flat mirror demonstrates everything that we need to know to discuss how to solve these problems. So you can see the image in this case, there's no surprise. We're looking down, we see the camera reflecting perfectly in the mirror, the ray angles coming from the light are striking the mirror, coming up to the camera and bouncing in between. So we're doing a very good job of imaging our camera and the things above the mirror, but in fact, we want to see the surface of the mirror. So this brings up the demonstrates the most challenge that we have with very flat specular surfaces. Conversely, we can now go and move the mirror and try and get the camera out of the view and do some things within our uniform light field to improve the situation. But you'll see that moving the object doesn't really help. As I move it and try and get away from my own reflection and try and create different angles, you'll see what happens is then we start getting angles where the light can actually strike the mirror surface and the light itself, it can be imaged into the camera because now there's very direct angles. So even though we have a uniform light field and we can move it out of the way of what we don't want to see, there's nowhere in the light field because of the highly specular surface and the structured light that's bouncing off of it, there's nowhere we can get in this uniform light field to achieve what we need to see. So I'm going to remind you of a previous slide from our bright field and dark field lights. One of the solutions for bright field lighting is a dome light. And in fact, we touched upon this very subject we're talking about today in the previous module where we're talking about bright field lighting, showing that sometimes when we have surfaces like the crinkled aluminum surface of this pudding cup here, that we can flatten out, or even the shiny lid from a baby jar, you can flatten out using a dome light. This is what a common solution for dealing with specular surfaces, not only the roughness, but the specularity, and applies today. So what if we take our problem with the automotive rear view mirror and apply the dome light to it? Well, you see, as when we were talking about this in the bright field presentation, that this works really good, and you can see this works because you're bouncing the inside of the dome. You're still imaging with very direct angles, but light is coming off the inside of the dome at all angles and striking very uniformly on the surface, and this works because the surface becomes very bright, white, and uniform as the inside of the dome, and it works because you're actually lighting up the surface uniformly with the reflection and taking advantage that we can make a very even reflection of the whole surface and get things flat and uniform. But you also see, we mentioned in the previous module about dome lights work good at this, but you have this problem where you see the hole where the lens is looking through and doing the imaging, often called a hole in the sky problem. One solution to this can be moving the mirror off center in this, and it does help with the hole in the sky problem, but it also raises some other considerations. So you can see the difference between this image and this image of the mirror is that we just moved it off center, took advantage that the hole in the sky is always at the center of the image, and by getting our mirror that we're inspecting off center, you can see we get a very flat reflection off there. However, this brings up some other considerations for this solution. The first part is we can only use half the image. If by definition we have to stay away from the hole in the center, then, and we put something like with a rectangular profile in here, we can only use the top half or bottom half or left or right half, depending on how you're orientating your image. But you can only use part of the field of view. So we're wasting some of the camera's pixels and field of view here. And the other consideration, you'll notice that we had a rear view mirror that had a specific shape to it. And if you look at the image here, though we have a very uniform, I actually let this problem occur to talk about it here. And you'll see we actually have the edge of the dome. This is no longer the corner of the mirror. The corner of the mirror is too dark to be seen here, but you're actually seeing the rounding of the dome in here. So this doesn't mean you can't solve this problem with a dome light, but what it does mean is the dome must be much, much larger than the object inspected. So to solve this, where I moved the mirror off center, got the image I wanted on the surface, but was seeing a little bit of the rounding, we would just have to move to the next bigger dome, create a little more good imaging space within the dome, and fit our object within there. But this would otherwise provide a very good solution. So you do have to consider these, and the fact that we're wasting the area and that the dome must be much larger. However, domes are still one of the most common and viable solutions for this, because the price of large domes are coming down, because the often used in the as solutions in the marketplace, the number and volumes of domes being produced are high. Therefore, domes are cheaper than other solutions that may be out there as we take the next steps to solve this. So sometimes, even though we have these special considerations with the dome light, a dome light still can be the best. And especially if your object were smaller and you're having these problems, consider a medium to large dome light. Just get the object out of center and you may get very much what you need to solve the problem. What we do if we do need to solve these problems and move on from a dome light because we don't want to deal with the loss of space or having to fit the object within the dome, is we move to more advanced solutions. And one of these solutions that SmartVisionLights offers is what we call a TL305 diffuse on and off axis light. This light, as you can see from the diagram, this is actually a tunnel dome. So though it's wide like a linear light, inside the surface is curved. So this is a specific what we call a tunnel dome. It's a form of dome light, and we have the light coming off the curved inner surface like any other dome. But inside we also have an on-axis source that is hitting a beam splitter. So this solves the problem. You can see in this case that on the bottom left, we have a pill blister pack, and you can see all the little reflections on the surface from the specular surface where it's capturing the light above. This light solves that by providing light that is diffused and would otherwise leave the hole in the sky problem, but we actually take the on-axis light, bounce it through the hole via beam splitter, and we actually fill the image area in the middle. So you can see the image that we actually achieve on the right is very uniform. There's no glare, and we can inspect everything because the hole in the sky is then filled. The TL305 I used for this example, but going back to dome lights, we also have similar solutions where we take a look at a product like our DADL75 RGB dome light. And in this case, we've taken our large dome lights, we've put what is called a coaxial light, which is essentially the same beam splitter and light, but in a discrete module. And this allows us to look with the camera straight, linearly on axis through here, use a bigger area. The TL305 presents a long, wide aspect ratio. The dome uses a circular area, but we no longer have the hole in the sky problem, because again, whether we use either of these, we're filling it in with the on-axis light source and get away from the problem we had. So if we come back and recap what we know here, we know a few things about light and how it interacts with the materials, and we can look at the surface of the material and classify it as specular or matte, reflective or absorptive, consider if refraction is going on, or more likely is somewhere in between all of these. But no matter what the surface is, our goal is to make it with a high signal to noise ratio. And in this case, the signal is the surface of the mirror that we want to see here, as opposed to the noise, which are things that are reflected in the mirror that we don't want to see, like our setup. So again, the structure of the light is important in this, whether we choose a dome light or otherwise, but also the fact that our surface was very specular drove us to have to also consider the object we're inspecting, as well as the geometry of the lighting, to get the right image. I just want to remind everyone here that SmartVisionLights is your partner in machine vision. If you have these kind of things, we hope that these seminars are helping you with your lighting. If you need additional help, we encourage you to come to us, bring your applications, and we will help show you how to get the image that you really need. We're here to help you win the business and get it right, and we will be your local experts. That completes today's presentation. Thank you and have a nice day.